We close this Module 1 with a lesson about Lewis symbols in the octet rule, and this is really where we've been trying to get through all these lessons leading up to this. This is where we're going to be able to, once we have Lewis symbols and an octet rule, we'll be able to step off and begin to form bigger things than atoms, molecules, and so forth. Our learning goals are going to include factors that influence the stability of valence electrons or their activity in atoms. We're going to learn about the octet rule as a governing principle for elements. And we're going to use Lewis symbols to represent the valence electrons in these elements, because that's really where all of the important action is. So, what is the importance of the valence shell? Well, electrons that are added or lost by an atom affect the population of the valence shell. So that is the most accessible shell of all of the shells in an atom. So it's going to be the most prone to adding or subtracting electrons. Those valence electrons are the most accessible to other atoms, so they could be stolen by another atom, or other atoms could donate electrons to a given atom. Elements that have the same number of valence electrons are found to have very similar properties and behavior, and we began to see this as we counted the number of valence electrons on the periodic chart. All of the elements in the same column should have the same number of valence electrons. So what is the stability of the valence shell? Why is it variable? What causes that? I want you to consider the ionization energy of sodium. Okay, sodium is element number 11. The first 10 electrons go into core electron shells, the first two shells, and there's only a single electron in the valence shell. Now, when we think about this single electron, the nuclear charge is very well shielded. It's plus 11, but there are 8 core electrons that are all shielding that nucleus. Right? What that means is that the valence electron is far away. It's in the third shell, so it's not feeling as much negative attractive charge to the nucleus. This means the ionization energy is going to be low. In other words, it's easy to remove that electron. I want to contrast that with the electron affinity of another element, fluorine. Okay, fluorine is 2 elements before sodium in the sequence, and it's element number 9. It has 9 protons in its nucleus and 9 electrons. Now, it has a valence shell vacancy, so there's an empty spot. It means that fluorine only has 2 core electrons, so it's not very strongly shielded at all. Those valence electrons, which don't shield each other very well, are all feeling a very strong attractive pull toward that nucleus. The nuclear charge isn't shielded well. Vacancy in the valence shell and electron affinity is going to be very strong. If there wasn't a vacancy in that shell, well, it may have been a different story. Okay, but if you can put an electron in there, it's going to feel that same strong pull toward the nucleus. I'll point out that both sodium and fluorine are highly reactive elements. They're known for their reactivity, and this is part of the clue as to why that's the case, because the ionization energy is low for sodium and the electron affinity is very great for fluorine. Now let's take a look in between. In between fluorine and sodium is neon. And you might ask, would it similarly be reactive, since fluorine and sodium are among the most reactive elements? Well, there are 3 Bohr diagrams. We've seen fluorine and sodium already, but let's take a look at neon. Neon's element number 10. It has only 2 core electrons, so it has a limited shielding there. Nuclear charge is poorly shielded. There is no vacancy in the valence shell. So in other words, all of the electrons that can benefit from having poor core shielding are already there. Okay, this means that their attraction to the nucleus is very strong. It's going to be pretty hard to rip them out, so the ionization energy is very high. There's no electron affinity, all because there's no place to put the electron. The next electron would have to go into the third shell, and it's going to find an atom that is very well shielded in terms of the core electrons, the 10 electrons that are already there. So it doesn't really attract another electron very easily. What this means in sum is that the valence electrons in neon are very stable. You can't pull one off. You can't add a new one to it. Neon likes to have 10 electrons, or 8 in its valence shell. All right, and it turns out that this is a very special observation. It leads us to the octet rule. It's a rule that basically says a filled valence shell is energetically favored by atoms. And it's easy to begin to see this now because those valence electrons are feeling a stronger attraction to the nucleus because they are not shielded as well. They have fewer core electrons. And there's no vacancy to add another electron, so it doesn't have a very good electron affinity. The noble gases are all inert, as I mentioned before. They are non-reactive because they have a filled valence shell. It turns out that other atoms will interact with each other so as to achieve a filled valence shell, so they can imagine, if you will, that they have a filled valence shell. And for second and third row elements, a filled shell means 8 valence electrons. Now you begin to see where this rule comes from and where the name Octet Rule comes from. Octet stands for the 8 electrons that would fill the valence shell. Now we can use this, and G. and Lewis used this some time ago, about 100 years ago, to create something called the Lewis dot symbols, which are just a pictographic way to represent the valence electrons of an atom. But they're a picture that helps us begin to see the similarities between atoms and understand how they interact with one another to form bonds. So let's look at an example. Simplest example is hydrogen. This is the Lewis symbol for hydrogen. It is this chemical symbol hydrogen with a single dot drawn. The dot represents the electron in hydrogen. So the atom is represented by an elemental symbol. Only the valence electrons are shown. Now, hydrogen only has one electron, so you're seeing all of the electrons, but in other ones, you'll only see the valence electrons. So let's look at the second column. Okay, it's actually the second column. Okay, so starting with beryllium, the element number 4, magnesium element number 12, and calcium element number 20. You can see that each of these has 2 electrons in its Lewis symbol. All right, we're only drawing the valence shell electrons, so each of them only has 2, but this really emphasizes why they have similar chemical properties. They have similar populations in their valence shell. Now you may be wondering, why did I draw the 2 electrons in beryllium on either side of the beryllium chemical symbol? And magnesium I drew one on top and one to the side, and calcium I drew one to the bottom and one to the side. In fact, all of these are equivalent ways of representing those 2 electrons. You don't have to put them in the same places each time. You can put them on different sides. Now, it is important that we separate them, that we don't put them together, and I'll talk about that in just a moment. But as long as you have 2 on different positions around the chemical symbol, you have a valid Lewis symbol. So it's pretty easy to reproduce. All right, so let's see how we would construct these. Some general rules. Okay, let's say that X is the chemical symbol of our atom that we want to draw a Lewis symbol for. We're going to imagine that there are 4 quadrants, each represented by those yellow circles or yellow ovals around the X. Each one of those can hold 2 electrons. Now it turns out they're representative of orbitals for electrons around an atom, and each orbital can only hold 2 electrons. But in any case, in the case of Lewis symbols, we can only put 2 in each of those quadrants. So the steps that we're going to follow is we're first going to write the elemental symbol. We're then going to determine the number of valence electrons that that element has. We can do that from the periodic table if we wish. We're going to place electrons 1 per quadrant until all of the quadrants have a single electron. And then subsequent electrons, we're going to add a second electron to those quadrants until we've used up all of the valence electrons. Okay, it's probably simplest to see this in action. So we're going to use oxygen, which has a chemical symbol O, pretty easy. And it has 6 valence electrons. So one possible construction, and this is a little bit of an animation, one possible construction of the Lewis symbol would look like this, where we put 1 in each quadrant first, then a second one in 2 of the quadrants. Now we have a total of 6 electrons. All right, and this is a valid Lewis symbol for oxygen. We also could have other correct Lewis symbols, and some of those are shown here. Notice that the thing they have in common is 2 of the quadrants have 2 electrons, and 2 of the quadrants have a single electron in them. All valid Lewis symbols for oxygen must show this. Okay, you can only double up electrons in a quadrant when you have put 1 in each of the 4 quadrants around an atom. So as long as you can figure this out. As long as you can follow these instructions for drawing a Lewis symbol, you should be good to go for any Lewis symbol I might ask you.